Hello everyone, hope you're doing well today. For this section, we are looking at the substitution rule for integration. Its main use is to reverse the chain rule of differentiation. So that is, if we recall that when we have a composition of functions, such as f of g of x, the derivative of that composition would require the use of the chain rule. We take the derivative of the outer function, leaving the inner function alone. Then we take the derivative of the inner function, multiply it by the derivative of the outer function that we just took, okay, and that applies the chain rule. Well, when we are doing an integral, by the fundamental theorem of calculus, we should be looking for an antiderivative, if an elementary antiderivative does exist. And if the case is that there is an antiderivative that we can find, okay, when we're looking at an integrand, which is the result of a chain rule, we would want to think of reversing that chain rule to find the antiderivative. And that is the main purpose of the chain rule. We're going to be performing a substitution. Usually the variable that we choose for the substitution is the variable u, so we oftentimes will call it the u substitution. Now, really we're choosing a variable that is not already the variable of integration. If the original integral is written with respect to x, or perhaps maybe with respect to t, which is quite common as well, then the choice of u is usually going to be the first choice that we make. So we call it a u substitution. However, in the chance that we might already be looking at a function where the differential is with respect to u, so if the integrand was already written with respect to u, then in that case we might want to choose a different variable. We would want to choose a different variable for our substitution, perhaps v. I want to make a note from the start where we're going to be looking for an appropriate substitution. Okay? U is a function of x, where u is a function of x. But we're never going to choose u is equal to x as a substitution. If we just exchange one variable for another variable in just a one-to-one change, u is equal to x and du is equal to dx, it's not going to change anything about the geometry of the problem. It's not going to transform the graph. It's not going to change anything else about how challenging it may be to do the integral. So we're never going to just choose the substitution where u is equal to x. That would do nothing. But what we'll be looking for, if we couldn't have already just done the antiderivative by some more elementary process, we'll be looking for combinations of x in the integrand such that we can set that equal to u, then differentiate that in order to find the differential du and see if that can help us to transform the integral. So here's how we can suggest that the u substitution actually reverses the chain rule. Consider if we had a composition of functions. I have here the big F of lowercase g of x, that composition. And I'm using the big F here because of what we're going to see in the integrand. Okay, so if we take the derivative with respect to x of this composition, by the chain rule, we would first then take the derivative of the outer function. And I've called the outer function big F so that it is the antiderivative of little f. Okay, so I've made that choice. So I'm saying that f of x is equal to the derivative of the big F of x. So big F is an antiderivative, in other words. So if we take the derivative with respect to x of this composition, right, we get little f on the outside. We leave the g of x alone. All right, so that was the first link in the chain rule. And then we multiply that by g prime of x. All right, that's our chain rule right there. Well, now suppose that this combination right here was then what we were asked to integrate with respect to x. That is, if we're asked in an indefinite integral, if we're asked what would be the antiderivative of this combination. The antiderivative of this combination, well, the answer we would expect to get back would be this right here, big F of g of x. That's what we expect to find as the antiderivative of this combination. Well, the u substitution process allows us to clean up this integrand, to reduce it down to where it just looks like this. We actually instead reconstruct it so that we have a function of u, and then we can integrate with respect to u. So it's a simplification. And then if we were to find the antiderivative of this, okay, the antiderivative of this, again, the antiderivative of little f would be would be big F. So this would give us back big F of u, where what was u? Well, we said u is equal to g of x. Okay, if we notice, we want to rewrite this as f of u du. Okay, so we can make the selection that the inner function, okay, is what we're calling u, and by that choice, notice through the use of differentials, the differential du would be found by doing g prime of x dx. Right, that's differentials right there. So by choosing this inner function g of x to call that u, then this product here, g prime of x dx, that would become the differential du. So we would transform this combination here into f of u du. And this is under the assumption then that this is going to give us an easier thing to integrate. Okay. So primarily here, I guess at the start, let's take a look at an example of a function whose derivative we would find by the chain rule, so that then we can take the antiderivative and see how the substitution rule could have helped. Okay, so let's find y prime if y is equal to the sine of pi x. Okay, so y prime would be the derivative with respect to x of the sine of pi x, and that derivative is done by the chain rule. First we take the derivative of the outer function. The derivative of sine is cosine, and then we leave the inner function alone. We leave the pi x, and then we multiply by the derivative of the pi x. Well, the derivative of pi times x would just be pi, because it's linear. So we get the cosine of pi x times pi, or another way to write that would be pi times the cosine of pi x. Okay? All right, so that would be y prime, the derivative, if y is equal to sine of pi x. Now let's reverse that process. Let's integrate to reverse what we just did. In other words, find an antiderivative. It should be that the antiderivative of pi times cosine pi x dx, right? If we write this indefinite integral right here, this is saying what is the antiderivative? We expect to get back this, the sine of pi x, right, to reverse the differentiation. We choose u to be the inner function. So we find out, is there a function within a function here, or where we can choose something to be u, and it's going to be important that we choose the correct thing for u, because if we choose an incorrect function for u, the substitution is not necessarily going to work. And how do you know what the correct substitution is? It's by practice and observation, trial and error, building an intuition that you have for how to do the integration strategy. And that's where we are in mathematics now. It is not necessarily a straight line approach. A little bit of ingenuity and being sometimes being clever and being willing to try something even if it doesn't work, where you have to then try something different, but you learn something from what didn't work. At least you learn something from that. That's really where we are right now. Okay, so for this example, I'm going to say we're going to choose to let u as a function of x equal the combination pi times x. That was our substitution choice, and let's see if it works. By making that choice, here's a consequence. As a result of choosing that function of x, notice u here is a function of x. Right? By making that choice, we can now find the differential du. Right? The differential du, which of course is going to be the derivative of this, that would be u prime of x and then times dx. So in this case, du is equal to pi dx. So this differential that we found here is a direct result, a consequence of the substitution function that we happen to choose for this example. Okay, now there's a couple ways in which we can incorporate our differential into here. First, if we can find the combination pi dx, that combination can be replaced by du. So notice here we have pi and we have dx, and that combination right there, pi dx, can be replaced by du. That's one way that we can do that. Okay. So if we replace pi dx by du, then I can just put du, the differential with respect to u, at the end of this. And then replacing cosine of pi x, well, Since we chose pi x is equal to u, then the cosine of pi x turns into the cosine of u. So we now have the integral the cosine of u du. Now, if we had bounds on here, if we had a definite integral, we would also have to, as a consequence of our choice of the substitution, we would also have to change the bounds to be values of the new variable of integration. And we'll take a look at some examples where exactly that occurs as well. Right now we're just dealing with the anti-differentiation part of it. So we've transformed it into this form. Okay. Now we can integrate with respect to the new variable u. And the integral of cosine of u, the antiderivative of the cosine of u, that would be the sine of u. And then because this is an indefinite integral, we have to add the arbitrary constant c. So we have the sine of u plus c. We got away from the integral now, right? We have a function as an answer. But this answer is with respect to u, right? Notice we now have some type of antiderivative function with respect to u as the variable. Okay. But what we want it to do is we want it to find the antiderivative to this. And the antiderivative to this is going to be a function, an antiderivative function of x, actually. Not an antiderivative with respect to u, but an antiderivative with respect to x. Because the original integrand was with respect to x. And for that reason, we need to transform our function here back into a function with respect to x. How do we do that? By returning to the substitution. We said u is equal to pi times x. So we go to our answer here, sine of u plus c. Well then, replacing u with pi times x, we get the sine of pi times x, and then plus c. And that gives us our antiderivative with respect to the original variable x. Now how can we check the answer? How can we check to see if we got the right answer? That is, how do we know that that really is the antiderivative of pi times the cosine of pi x? This is the antiderivative if its derivative, if the derivative of our answer gives us that integrand. So the derivative of the sine of pi x plus c is going to be the cosine of pi x times pi, there's our chain rule right there, and then plus 0, because the derivative of the constant is 0. So we get back pi times the cosine of pi x, and that was our integrand. Okay, so that's how we know that we got the answer correct. Back in terms of the original variable, okay, we performed a substitution which had a consequence of a new differential quantity coming along. And we had to replace both the instances of x in the integrand and the differential itself. Every instance of x within the integrand and the differential, every one of them needs to be replaced somehow by the use of the substitution we choose. Now, once we choose our function for u of x, once we make this choice, again, that comes along with a consequence of the differential we're going to get. So we don't have independent control over the differential. The differential is dependent on the choice that we make for the function u. And if there were other instances of x floating around in here, well, we'd have to find ways in order to make the substitution work with that as well. And we'll take a look at examples like that. Okay, more complicated looking examples than this. But this demonstrates that this does work. It allows us to find an antiderivative when the function in the integrand would be the derivative through the use of a chain rule process. So the u substitution is a way to reverse the chain rule. Now there is another way in which we can do the substitution for the differential du that I'd like to point out here. Once we have du in terms of dx, we can choose to solve that. We can always choose to solve that for dx. All right, so let's take a look at how that would look right now. If du is equal to pi times dx, notice that that means that du over pi is equal to dx. And then if we went back to the original integral, and if we chose to replace it that way, right, then the original integral we had pi, and then we had cosine, and then pi x, well, that was what we chose u to equal. So, of course, that gets just replaced by u. And then dx itself now, the original dx can get replaced by du over pi. Okay. And then by doing that, we're going to end up simplifying to the same result we had before, because here we're going to be able to cancel this pi with this pi. Okay. So this is going to simplify as the cosine of u, du, and then we're back here again, right? and so we'll get exactly the same answer. So that is, when you find the differential, sometimes it may be clear from the integrand that maybe you already have exactly the product that you found in the differential, but you don't have to necessarily find that product. Sometimes solving for the dx, or some combination within there that you do have, so that you get dx with respect to du, you can do the substitution that way instead. And sometimes it'll help to clean up the integrand. Okay. And as long as you do that process, the substitutions, algebraically correctly, okay, then it'll work out the same in the end. So there's a combination of algebra strategy here and calculus strategy. Right? So, of course, the calculus would be included with finding the differential. You need the derivative to do that. And then finding the antiderivative after the substitution is complete. That's the calculus part. But the algebra part is recognizing how to choose the function for u, okay, to try to find that inner function that's going to make this work, and then to actually perform the substitution. Furthermore, there are times where we're going to want to invert our substitution. Just as I just mentioned here and showed that once you have the differential, you can choose to solve for dx in terms of du. We can do that because of invertibility, essentially. And we can solve it for one of these differentials or the other. We can do the same with our original substitution, u equals pi times x, for instance, if needed. If there was another instance of x somewhere in this integrand, we could replace every other instance of x, in this case, by u divided by pi, by solving our substitution for the other variable, for the variable x, instead of for the variable u. And sometimes we're going to want to do that in combination. Okay, so that's the use of algebra, okay, within the substitution process. Okay, take a look at the notes over here. I show you our substitution rule for indefinite integrals, as was just demonstrated in that example, and the substitution rule for definite integrals right beneath it. Okay, the difference being, with definite integrals, we have bounds. Recall, from geometry of this, when we take an integral and we have the bounds a and b, that would be the left bound and the right bound of the region for which we're looking for the net area, right? For the function to be bounded from x, the variable of integration x equals a, to x equals b. X equals a and x equals b. So we can recall that it's helpful maybe to reference that this dx is telling us the variable of integration, which is exactly what this bound and this bound, okay, are representative values of. Okay. Let's take a look at that definite integral and a substitution. So we have, there you go, for definite integrals. For definite integrals. So we have the integral from a to b. Okay, we have our f of g of x times g prime of x dx, okay, is going to become an integral where we have f of u du for the integrand part and the differential part, as we just showed. Okay, but to figure out the bounds, if dx, okay, is the differential, then that means that x is equal to a and x is equal to b. Okay, it means that x is equal to a and x is equal to b. So those original bounds were values of x. And x is the variable of integration. Well, similarly then, the values of the bounds over here must correspond to the variable of integration here. They must be values of u. We can't put a and b here because a and b have already been used and those were values of x. So we have to find out, well, what are the values that we should be putting here? Well, if we're letting u equal to the inner function g of x, okay, that is, for any value x that we can plug in the domain of g, we're going to get an output u. Okay, so we get, for instance, if x is equal to b, then up here we're going to have g of b, right? Because that would be the value of u when the original upper bound was plugged in. So this is a value of u right here. And similarly down here, we would plug x is equal to a into our substitution that we selected. So another consequence of the choice we make here, we plug the lower bound into our substitution to get a new lower bound. And then we would continue with the integral as normal. There can even be cases, based on the transformation that happens to be selected, that happens to work, there can be cases whereby it could have been that A is less than B. It could be that A is strictly less than B over here, as we would normally expect. But there can be cases whereby the resulting G of A ends up actually being greater than G of B. Even things like that can happen. Nonetheless, whatever the transformation that we choose, however it tells us to map A to U, right? In that way, we're going to change this lower bound, the original lower bound, to this new lower bound, even if this number ends up being greater than that one. Now, how we deal with the fact if they do reverse, if we end up with a larger value on the bottom as opposed to the top, recall that if we have an integral from A to B, we can flip the bounds. We can make it from B to A of f of x dx. We can always flip the bounds by changing the sign of the integral to negative instead. And that's how we would deal with any situation which might cause us to switch the order of the bounds. Okay, just in case that might happen, because it does happen in certain cases. Okay, and as you move into calculus 2, you're more likely to run into those cases, certainly. All right. Okay, so it is important to note again that the bounds that we write, they must correspond to the variable of integration. That is very important, okay, so that we are in agreement here. When we are making the choice of the substitution, as a consequence of that, we get the differential, and we also get the new bounds. Okay, so consequences of this choice, du is going to be g prime x dx. And the value of u at the top is going to be g of b, and the value of u at the bottom, the lower bound, is going to be g of a. All of these three things are consequences of the choice we make for our u substitution. And that's then how we deal with a definite integral. One other thing in this section to take note of, as it turns out, is that also we can use symmetry, the even and odd symmetry of functions, in order to help evaluate in certain cases. Now, it requires, to use the symmetry, it's going to require that we also have a symmetric closed interval, symmetric over 0. Okay, so negative a to positive a, and so 0 would be right in the middle of that. And if we're integrating an even function over that symmetric interval from negative a to a, then that means we're going to be doubling the area of just one side of that function, either 0 to a or negative a to 0. And that's because of the geometric symmetry of the curve. It's symmetric over the y-axis is why. Is the reason why. If the function is odd, then due to the symmetry of an odd function, the integral from negative a to a is always going to be 0. Okay, let's take a look at an example like that. Okay, different types of symmetry. And then we'll get back to the substitution idea. And sometimes that notion of symmetry can just be a helpful a simplification for certain integrals. Okay, here we go. Take a look at a couple symmetric integrals. Okay. Let's say, recall, the function y equals x squared is an even function. Okay, in fact, I'll call it f of x. Okay, the function f of x equals x squared is an even function. And that's not because the power is 2, by the way. For instance, if I write the function f of x is equal to x minus 1 squared, this function is not an even function. That's not even at all. What makes this function even is that f of negative x is equal to f of x. What is f of negative x for this case? F of negative x would be the quantity negative x squared, and f of x is just x squared. And of course, the quantity negative x squared is equal to x squared because the square of a negative would always yield a positive. All right? So for a negative real number squared, we get a positive real number squared. Okay? And of course, the square of 0 is 0. Okay, so this is true. Now, why is this true geometrically? If we were to graph the function f of x is equal to x squared, all right, recall that every point on the graph, let's try to make it look like it's got that symmetry. For every point we choose on the graph, let's say I choose a point to the right of the y-axis. That point has coordinates where for whatever the value of x is that we plug in, the value of y is going to be x squared. Right? For instance, a point like 3, 9 would be on the curve. Right? Well, if we went to the opposite side of the y-axis and chose exactly the opposite of that x, right, the associated point would have that opposite x, and that opposite of x would be squared. For example, -3, okay, when we plug that into the function f of x equals x squared, plug it into the function f of x is equal to x squared, you get -3 squared, which is positive 9. And of course, as we can see, 9 is equal to 9, right? They're symmetric over the y-axis. Okay, symmetric over the y-axis. All right, so if we were to integrate the function from -3 to +3, for example, of x squared dx, what would we get? And if we interpret this in terms of net area, okay, so we're saying this area, that would be, in this case, from -3 to 0, is exactly equal to this area by symmetry. So from -3 to 3 of x squared dx, that's 2 times the integral from 0 to 3 x squared dx. Notice how that's true from the graph, and it's true because this interval from -3 to 3 is symmetric about 0. Okay, so note that -3 to 3 is a symmetric interval over the value where x is equal to 0. So that's, in general, -a to a. Okay, if we have the integral from -a to a of a function f of x dx, if f of x is even, then this is going to be double the integral from 0 to a of f of x dx. Okay, what would this be? 2 times x cubed over 3, 0 to 3. So it's going to be 2 times, it's going to be 3 cubed over 3, and then it's going to be minus, that's going to be just minus 0, right? Minus 2 times 0. Okay, so this is going to be 2 times 9 is 18. So the answer is 18. And because we were able to evaluate it at 0 at the lower bound, it made it really, it made it easier, a little bit easier for us to evaluate the integral overall instead of having to use the -3. All right. Now, what about an odd function? Recall, f of x is odd. Okay. Let's see. Which is a function, an example of a function that is odd? Oh, how about the sine function? F of x equals the sine of x is an odd function. That is that f of -x is equal to -f of x. All right, take a look at the sine function. All right, so there's our sine function, at least a portion of it. Right, continues outward. For any point that we may choose out here, for instance, if we have the coordinates x, f of x, at that point, where x sine of x for this particular function, okay, there would be another point where if we went to the opposite side of 0, if we went to where -x is located, right, the output of the function would be negative of this f of x. Right? It would be negative of that f of x, and another way that we could write that is we could say, well, this is also going to be f of -x, for instance, right? So this is at the point with coordinates -x sine of -x. But in terms of areas, like when we're looking at the integral for this function, if we wanted to integrate it from -x to +x, notice that we would be taking this area here and subtracting that from this area here. which notice by rotational symmetry, if we were to rotate this around by 180 degrees, this area exactly overlaps that area in size. These are the same size areas, but the one above the x-axis is a positive. We take it as positive, and the one below the x-axis we would subtract from the one above the x-axis. So the integral from, well, let's take an example. Let's take the integral from, all right, let's say this would be pi over 2. This would be pi. Let's say it's from like negative 3 pi over 4 to positive 3 pi over 4 of the sine of x dx, for instance. Okay, so we have an interval from negative 3 pi over 4 to positive 3 pi over 4. Okay, and that is, again, symmetric over the value where x is equal to 0, so it goes as far to the left as it goes to the right. Okay. And the function f of x equals sine of x is an odd function, so this is just going to equal 0, and we're done. Now, if we wanted to actually go ahead and evaluate the integral, we can take what the antiderivative for the sine of x is negative cosine of x, and then we can evaluate it from negative 3 pi over 4 to positive 3 pi over 4, okay, and then you can evaluate that. Negative cosine of 3 pi over 4, and then we're going to subtract the negative cosine of negative 3 pi over 4. So that is what? Negative, and the cosine of 3 pi over 4 is negative root 2 over 2, and then we get minus minus, which is a plus, and then the cosine of negative 3 pi over 4, the cosine of negative 3 pi over 4, that would be in quadrant 3, and that would be negative root 2 over 2. So we have root 2 over 2 minus root 2 over 2, and so that is just going to equal 0. So this is a shortcut. If we notice that we have an odd function in the integrand, and if we are integrating over an interval that is symmetric over 0, then the output would always be 0. And we can see that that's geometrically so by doing a sketch of an odd function. Okay. All right, so if we have the interval from negative a to a, the interval negative a to a, right, then the integral from negative a to a of f of x dx is equal to 0 if f of x happens to be an odd function. Okay, so that could be something that helps to serve you well in doing integration for some examples in the future as well. Okay, let's get back to our substitution rule. Take a look at a more complicated example. Consider this example from the type notes. The integral of 2x over x squared plus 1. It is a quotient, and we do not have a rule to reverse the quotient rule, so we shouldn't be looking at this as if we take the antiderivative of the top and the antiderivative of the bottom. Furthermore, algebraic simplification doesn't work. For instance, we can't divide 2x by x squared and 2x by 1. That is algebraically incorrect. We're stuck with the function looking like this, and we have to find a way to integrate it in this form. Okay, but we can't use some reverse of the quotient rule. So we search for, is there a portion of this expression that we can choose by use of a substitution, also bearing in mind that the differential of that choice, okay, could be beneficial to us here. And we have to be able to do a substitution where every instance of x, including dx, is transformed into instances of u and du. We can't leave an extra x floating around in the integrand. So we need to figure out some choice of a function here that is going to work for all of those. Okay? And the choice of the substitution that works for this example, when we take a look at the denominator, it's x squared plus 1. And if we think of the differential, that is the derivative, let's think of the derivative of x squared plus 1. The derivative of x squared plus 1 has 2x. Now the 2 is there as well, but even if the 2 wasn't there, we could still do the same substitution. The derivative of the x squared will give us a linear function. It will give us another x. And for that reason, we're going to make that choice. And it'll give us the dx as well. So now we try the substitution u equals x squared plus 1. And the differential du then is equal to 2x dx. So we can either replace the 2x dx that's already in the integrand by du, Or we can choose to solve for dx to get dx equals du over 2x. And then we can replace dx by du over 2x. We can replace x squared plus 1 by u. And then the remaining 2x, fortunately, cancels out. And that's what we want to have happen, because we need to be able to rewrite the entire integral with respect to the new variable. There should be no more x's floating around. There could be constants in there, but there can't be any more instances of x. And we also need to include the differential written every time. Okay, so we are indicating which is the variable of integration. And I make that note up here that it is important that we are paying attention to the differential that tells us the variable of integration. So for example here, when I write the integral of x dx, that would equal x squared over 2 plus c. That would be the antidifferentiation for that. But if it was the integral of x dt, that dt is telling us that the variable that we're interested in is t right now. That's the thing would be in motion. T is in motion, not x. So x is treated as a constant. So the integral of x dt is different than the integral of x dx. Right? The variable of integration does matter here, the differential we choose. So we start it with a differential dx, and we are transforming this integral into an integral that has a differential du. The integral of 1 over u du is the natural log of the absolute value of u. Remember, you must have the absolute value bars when you do the natural log, especially when we don't know information about the bounds, and also very important if the bounds might happen to be negative. That's the purpose of the absolute value there, so that the domains match. But then we have to get this back in terms of the original variable. Okay? And so that's what I'm doing here. I do a little more explanation down here. I'm transforming it back in terms of the original variable, replacing u with the x squared plus 1. Now to check to see if this is correct, that is the integral of this, which is a general antiderivative, is the integral of this equal to this function here? We can find out by differentiating our result. The derivative of the natural log of the absolute value of x squared plus 1 plus c would, in fact, by the use of the chain rule here, 1 over x squared plus 1 times 2x, by the use of the chain rule, does give us back the original integrand. Now, if we were to include bounds in this example, we could then integrate this function with respect to those bounds. And we should choose bounds that are within the that are within the domain of the integrand. Now, what is the domain for this integrand? The numerator is 2x, that's polynomial, and that's all real numbers. The denominator, being x squared plus 1, is also polynomial, so that's all real numbers. Furthermore, the denominator cannot equal 0, but x squared is not negative for any real number, and then adding 1, the denominator will always be positive. So this integrand has a domain of all real numbers. Okay. Let's take a look at how we could apply substitution in the case where we had a definite integral then for this example. Now we already know what the antiderivative is. We can apply then the fundamental theorem of calculus to do the definite integral. Okay, so let's take, for example, in the integral of 2x over x squared plus 1 dx. And now we can choose all real numbers for the domain, right? The domain, all real numbers. So we could choose anything. All right, so let's say I choose, how about from -3 to 5? Okay, so I'll do that. I'm not using symmetry here on this example. If you do have a symmetric interval here, if it was -3 to 3, it would be worth your time to check to see if this happens to be an even function or an odd function. All right, remember, you can check to see if it's even or odd by checking what is f of negative x and compare it to f of x. And to check that it's odd, compare f of negative x to negative f of x. Okay, if either of these are true, you have even or you have odd. And that might be helpful in then simplifying. Certainly if it was odd. If it was an odd function, hint, it is. Right, if it was an odd function and if it was over a symmetric interval like -3 to 3, you don't have to do anything else. You just say the answer is 0. Right, that would be convenient. Okay, but we need to now perform the substitution. So, substitution we already know. U is equal to x squared plus 1. Okay, in fact, I'm going to make one more change here. This is the change I'm going to make. I'm going to make this a 3x. What's going to happen now? 3x over x squared plus 1. Still going to choose u equals x squared plus 1. And then the differential du is still going to be 2x dx. And if I solve this for dx, then this is du over 2x, right, is what dx is equal to. All right? So I can change out this integrand then in this way. Let's see. So the 3x is still there for now. The x squared plus 1 gets replaced by u. And dx gets replaced by this, du over 2x. Okay, now that allows us to cancel out the variable x, and that is primarily very important. We need to get rid of all instances of x in the original integrand. But we didn't cancel out the 3, and that's okay because the 3 is just a constant. We are going to be able to factor out the 3 and the 2 in the denominator as well. And the integrand is going to be a du over u. But what about the bounds now? Okay, we need to figure out what the bounds are. Okay, so the upper bound, okay, is going to be, we said before that the original upper bound was a value of x, and the original lower bound was a value of x. So we have x equals -3, and we have x equals 5 as the bounds. But we've transformed now to where the bounds have to be values of the variable u. Okay, so how do we find out what those values are? Through the use of our substitution. All right. So the upper bound, where we now have, we have u is some function of x. Right? In the notes it says u is equal to g of x. So u is a function of x. So we can plug in a value of x from the domain and find a value of u from the range, okay, the range of g of x. So the upper bound would be g of 5 then, right? That where this is the function g. So this is going to be right here, g of 5, and down here we're going to have g of -3, right? Where this right here is our function g of x. Okay? So we are plugging these x values into our substitution to find out values of u. All right? So we have for the upper bound, if we plug in 5, then we're going to get 5 squared plus 1, which is equal to 26. So the new upper bound is 26. And for the lower bound, we're going to plug -3 into this substitution function. So we're going to get -3 squared plus 1. That's 9 plus 1, and that gives us 10. So the new lower bound is going to be 10. Now the substitution is complete. Now we have fully transformed this integral from an integral with respect to x into an integral with respect to u. So at this point the substitution is complete. And now we can perform the integration by the fundamental theorem of calculus. Part 2, we can find an antiderivative to 1 over u, right? This integrand is 1 over u du. Right? So we have 3/2 integral 10 to 26, 1 over u du. Okay? And the antiderivative of 1 over u is the natural log of the absolute value of u. And then we can plug in u is equal to 10 as the lower bound, right? And u is equal to 26 as the upper bound. And then we can go ahead and just evaluate this thing. All right? So 3/2 times the natural log of 26 minus the natural log of 10. And since both of those values plugged in are positive quantities, we don't need the absolute value anymore, right? Because they are within the domain of the natural log function. And that's it. You can leave our answer like that. We can also combine by laws of logarithms, right? Natural log of a minus natural log of b is the natural log of a over b. So we can write the answer like that, and that's fine. Alright, so that's how we can deal with a definite integral through the use of a u substitution, right? We have to change the bounds. Okay, here's another example right here. Here I'm choosing this function 2x cubed minus 1. Because, alright, so algebraically, we could expand this. We could take this to the 4th power by doing a binomial expansion, and that's going to give us a lot of terms in the expansion. And then distribute the x squared. That would be very expensive algebraically to do so. To fully expand this. Okay, through binomial expansion, then distributing x squared. But we could do that. Okay, but there's a big price to pay there in the algebra. Alright, so the u substitution helps us here instead to transform this, okay, in this way. If we take u is 2x cubed minus 1, because the differential du will contain an x squared in it multiplied by dx, that's why this is useful, because we do have an x squared multiplied by the dx. If I solve it for dx, I get, well, dx can replace then by du over 6x squared, and then the x squareds will cancel each other out, leaving us with a 6 in the denominator. That's why we have a 1/6 here. Okay, and then we have to replace the bounds. Okay, so we had x is equal to 1, x is equal to 0, and here was how we can find u. So when x is equal to 1, we get u is equal to 2 minus 1, which is 1. And when x was equal to 0, we get u is equal to 0 minus 1, which is negative 1. So the new bounds would be from negative 1 to positive 1, and we end up, after the substitution is complete, 1/6 times the integral negative 1 to 1 of u to the 4th du. And now the general power rule can help us complete this exercise. So u to the 5th over 5. Also, we can notice here, we are integrating an even function here. U to the 4th is an even function because if you take negative u to the power of 4, it's the same as u to the power of 4. And we have a symmetric interval from negative 1 to positive 1. It's a negative a to positive a. So when we have a symmetric interval of an even function, we can double the integral from 0 to the upper bound. Okay, so it's another way we could have evaluated it. So explain that right here. So this integral right here, because this is an even function and we have a symmetric interval about 0, we could instead write this as the integral where we have 2/6 or 1/3 from 0 to 1 of u to the 4th. And notice the answer comes out exactly the same. Geometrically, we understand why that has to be so for an even function. Okay, I have one more example here in the type notes, which demonstrates how we can simplify a horizontal shift by the use of a u substitution. So here it's not necessarily it's not really a reverse of the chain rule in this case, but it is because there is this shift. In this case, I have in the function, in the square root of x plus 2 function, that is a horizontal shift by 2 to the left if we were to graph y equals the square root of x plus 2. And I want to remove that because the integrand, the way it's written right now, would be quite difficult to find an antiderivative for in this form. We can't simplify it algebraically right now. If we wrote x as the square root of x squared, we could distribute it in here. Then we get something like the square root of x cubed plus 2x squared. That's not really any easier to integrate either. Trying to integrate it as a product would require techniques that we haven't discussed in this course and you'll discuss in your next course to deal with the integral of a product. And if we can avoid that process, it would be better if we could do so. So here's how the u substitution is going to help. By inverting our substitution. If we take u is equal to x plus 2, then we can invert that. Notice that this is a one-to-one function. It is invertible. And most important, that it is invertible on the domain of interest. And the domain of interest right now in the integral is from negative 1 to 2. Now, u equals x plus 2 is a linear function. It's invertible over all real numbers. But if we were choosing a substitution, think of substitutions where we have to restrict domains, like trigonometric functions. If you had to make a substitution through the use of a trigonometric function, and then if you wanted to invert that substitution, that type of instance would require that you check carefully where the interval is of interest for the integral. All right, so that you know that your function is truly invertible over that interval. Otherwise, you're going to have to look a little further into the exercise, like maybe split it up into multiple integrals. It'll create a more complicated exercise. But we are inverting here. That is, we are solving for the input variable and calling it the output variable, right? We're solving for x instead of u. And what that does is it allows us to we are able to replace what's in the radical with just u, so this turns into the square root of u, and the x that's in front changes into u minus 2. And we also have to change the bounds. Again, we have to change the lower bound and upper bound to values of u. Okay, but take a look down here at how that transforms the integrand into something that we can work with now. U minus 2, the quantity u minus 2 has the square root of u. We can now distribute the square root of u, something we couldn't have done up here. We distribute the square root of u, and we actually end up with a difference in power functions. And then the integration is easier that way, because now we can use the antiderivative rules for power functions. It is very important, though, that we also change the bounds. The new bounds, 1 and 4, those are values of u. We started with negative 1 and 2. We need to change into new bounds. But performing a substitution has created an integral that is easier to do. So doing that substitution in the associated algebra has made the resulting calculus easier. And then I complete the exercise here to show you how you can use power rules, fundamental theorem of calculus, part 2, and you can find the output for that definite integral. Okay? Practice a variety of examples to build your intuitive sense with integration. You're looking for opportunities where a substitution can simplify the integrand and make it easier for you to do the calculus, that is to do the integration part. Is easier said than done. Okay? In general, you're looking for reversing of the chain rule, whether to find an antiderivative, that's an indefinite integral, okay? Or whether to find the net area geometrically, that's where you're using a definite integral. Okay? You're trying to find easier ways to integrate, or in fact any way at all. If you're reversing the chain rule, you need to use some kind of a substitution in order to do so. All right, let's try another example here. Let's take an indefinite integral, e to the negative 1 over x squared dx. Okay. So from experience and practicing with a lot of integrals, okay, it can become more clear to recognize really through the use of differentiation rules, knowing like what might you choose as a value of u here, and bearing in mind what would be the resulting differential, and does that help? In this case, choosing something like u equals x squared will do nothing for us, because the du equal to 2x dx, nothing we do with that differential is going to be able to get rid of this x up here. I mean, if we tried to maybe if we tried to replace this with x is equal to the square root of u, then we have to consider, is it plus or minus the square root of u, because we have to consider the domain of this function. And the domain of this is all real numbers except for 0, so we would need a plus or minus. This creates a more complicated looking thing here. So this is certainly not going to work. Okay? But from experience with how we do derivatives, here's what I could suggest. What if you take something like u is equal to 1 over x? Or how about if you take u is equal to negative 1 over x? Okay, that is, u is equal to negative x to the negative 1 as a power function. What's the differential? du. Well, that's going to be positive 1x to the negative 2, and then dx. In other words, it's going to be dx over x squared. And that's great, because we do have a dx over x squared right here. Okay, so I'm going to take that. So dx over x squared, this combination here is going to get replaced by du. And e to the negative 1 over x gets replaced by e to the u. All right, negative 1 over x, that's u. So we have e to the u du. And that's a whole lot easier to integrate. The antiderivative of e to the u is e to the u. And because this is an indefinite integral, we need to add an arbitrary constant c. Now, since the original integrand was a function with respect to x, the output of this should be some function, some antiderivative function with respect to x as well. Okay, it would have to be. So we need to write our answer with respect to the original variable x. And that's done by reusing the substitution. Since u equals negative 1 over x, then e to the u plus c is e to the negative 1 over x plus c. And that's it. And we can certainly check our answer. The derivative with respect to x of e to the negative 1 over x plus c, we would need to apply the chain rule to do that. The derivative of e to the negative 1 over x is e to the negative 1 over x times the derivative of negative 1 over x, and then the derivative of the constant is just 0. So we get e to the negative 1 over x. The derivative of negative 1 over x, we did that up here, right? The derivative of negative 1 over x is 1 over x squared. So e to the negative 1 over x times positive 1 over x squared. In other words, e to the negative 1 over x squared. And that's what we started with. So that seemed to work. Okay. And if there were bounds, if this was a definite integral, a couple things would have changed. If this was a definite integral, we would want to change the bounds as well when we perform the substitution. So we would rewrite the new integral and we would do new bounds there. Another thing that would change, we wouldn't need to have the general antiderivative plus with the plus c. We We could just choose c to equal 0, for instance, because by fundamental theorem of calculus part 2, it doesn't matter which antiderivative we choose. Right? And then we would evaluate from the lower bound to the upper bound by the fundamental theorem of calculus part 2. And the next thing that would have changed, we would, if we had a definite integral, if there were bounds, once we change those bounds into values of u, we don't have to change them back into values of x again. Because we're going to get the same numerical value, right, by using those values of u as we would have if we had gone back to x's. So there would be no need to revert back to the original function with respect to x. So some differences that there are between an indefinite integral and a definite integral. Okay, and there's some flexibility there. But one thing we're not flexible with is if we had something like a and b in the original integral, we do not put a and b in the transformed integral because a and b, those were values of x, not values of u. And that's something we can't be flexible on, because notationally that would be incorrect. Conceptually incorrect as well. Alright, let's check another example. Here's a classic. What is the integral of the tangent of x dx? I haven't done this one yet. I mean, we know that the integral of the cosine of x dx, that's equal to the sine of x plus c. And the integral of the sine of x dx, that would be negative cosine x plus c. We know that. But what's the integral of the tangent of x dx? Well, here's how we can do that. We can start by using a trigonometric identity. Tangent is equal to the sine of x over the cosine of x dx. Right? So that's the use of a trig identity. Why is that helpful? Look for a u substitution. Can you find a function u such that the differential, the du, is going to be something that is multiplied by dx? Right? Whenever you choose u as a function of x, the du would always be the g prime of x times dx, right? You should note that the differential, if it's going to help you as a sum function of x, it should be multiplied by the dx. So although, if we choose u is equal to sine of x, we get du is equal to the cosine of x dx, this doesn't work. It doesn't work because the cosine is not multiplied by the dx. Instead, the cosine is in the denominator, and we can't force this to work. Okay, it's not going to work. What can we choose? We can choose u is equal to the cosine of x, the one in the denominator. Then the derivative of that is similar to the numerator, right? It would just be negative, right? Negative the sine of x dx. Right? And if you choose, you can solve this for dx. You get dx equals du over negative sine x. So this integral, then, let's do the substitution then. So we said u is equal to cosine of x. So that's the denominator. So the denominator becomes u. And then we have that dx is du over negative sine x. Okay, so dx gets replaced by du over negative sine x. And the original sine x hasn't gone anywhere yet. But now, by virtue of the substitution with the differential, we're able to cancel out the sines of x. We could factor out the negative, so we get negative the integral of du over u, which is the same as negative integral 1 over u du. So we get negative. The antiderivative of 1 over u is the natural log of the absolute value of u. We need the absolute value there. We don't have bounds here, so we don't know if we might be plugging in a negative quantity. And plus c. But now let's get this in terms of the original variable x. Okay, by reversing our substitution here, reusing, I should say, you're using our substitution. U equals cosine x. So this is negative the natural log absolute value of the cosine of x and then plus c. And we can check to see if that's correct. We can also rewrite this another way. Using a law of logarithms, we can move the coefficient to the exponent here, natural log of the absolute value of cosine x to the negative 1 plus c, which is equal to the natural log of the absolute value of 1 over cosine x, which is secant x, plus c. And that would be, therefore, the antiderivative, the general antiderivative to the tangent of x. Well, let's check to see that that's correct. by taking the derivative with respect to x. Natural log of the absolute value of the secant of x plus c. Recall that the derivative of the natural log of the absolute value of x is equal to 1 over x. Right? We checked that the natural log of x, its derivative was 1 over x, and the natural log of negative x, through the use of the chain rule, its derivative is also 1 over x. So the derivative of the natural log of the absolute value of x is equal to 1 over x. So the derivative of the natural log of the absolute value of secant x, that requires the chain rule, right? It requires the chain rule, which we reversed by the substitution here. So we get 1 over secant of x, not 1 over absolute value secant x, just 1 over secant x, times the derivative of the secant of x. And then the derivative of the constant is 0, so we get plus 0. So we have 1 over secant x, and then what is the derivative of secant x with respect to x? It was secant x tangent x. The secants cancel each other out, so this just simplifies to equal the tangent of x, and that's what we wanted. That was our original integrand, was tangent of x. So the integral of the tangent of x, through the use of a trigonometric identity and a u substitution, the correct substitution being u equals cosine x, we get either negative natural log of the absolute value of cosine x plus c, or the natural log of the absolute value of the secant of x. Okay, we're trying one that's maybe a little bit more challenging now. The integral of 3e to the x over 2 plus e to the 2x dx. So for this one, I want to make note that, let's see, the 3 in the numerator doesn't have to be there. We can factor that out. And we have an e to the x over 2 plus e to the 2x dx. And then we can recall by rules of exponents, something like e to the 2x, well, that's e to the x squared. So notice the form of the integrand is that we have something, right? We have some function over a number plus that same function, but it's squared, something like that. And that sort of looks kind of like, almost like it's trying to be with the something, with a number plus something squared. It kind of resembles like an, sort of like a function like 1 over 1 plus x squared. Do we know what the antiderivative to something like a 1 over 1 plus x squared might be? Well, let's see if we can do a transformation to this one. Well, we're not going to use x because x is already being used, but we can choose u. Let's let u equal to the thing that's getting squared here, which is e to the x. How do I know to make that choice? I just tried to explain it by recognizing the general form of this thing and sort of hoping that it was going to work. And you try it out, right? And you build an intuition by practicing more examples of this type. And just by changing this, by the way, just a little bit, if I change this to a 2x right here, all of a sudden the substitution that we're going to try now is not even going to work. It changes everything about the integral. And it can create a situation by a little change like that to an integrand. You can go from an integral that's easy to an integral that's challenging to an integral that's very challenging to an integral that is near impossible to do, just by little changes in the integrand there. Okay? So you have to be careful about creating these examples. Otherwise, you'll create an example whereby you would need to have completed your next semester of calculus to even attempt it. Okay? Just by little changes. Let's let u equal to e to the x. Consequence of that, the du. Du is e to the x dx. Okay, there's an e to the x and a dx. We could also solve this for dx and get du over e to the x. Either one, whichever one is easier for you. Okay. All right, so now we have 3 times the integral. I'm going to leave that e to the x on the top, so I'm going to replace dx by this. Du over e to the x. That cancels those. And then 2 plus e to the 2x is going to become 2 plus u squared. Right? Because again, e to the x squared is e to the 2x by rules of exponents. So now, this e to the x cancels with this e to the x. Right? We have something almost of the type integral 1 over 1 plus u squared du. If that's what we had, what would we get? The integral of 1 over 1 plus u squared du, That would be the arctangent of u. Okay? And that's what I'm looking for here. But we don't have a 1, right? We don't have a 1 right here, though. We have a 2. So how do we get that 2 to turn into a 1? By factoring it out from the denominator. So now I'm going to make the coefficient in front 3/2. We have factored out the 2. Okay, factored out the 2 from the denominator. So now the numerator is just 1. We have a du, or you could put the du on top. It would be the same thing. And the denominator now, after factoring out 2, this becomes a 1 plus, and we have factored out a 2 from the entire denominator. So if we were to redistribute the 2, we would have to get back a u squared. That means this turns into u squared over 2, like so. So now this can be written as a quantity squared. So we could do this. We could write this as 1 over 1 plus the quantity u over root 2 squared du. So now we have a 1 over 1 plus something squared. And now I'm going to do something else. I'm going to choose another substitution. But since u is the variable of integration here, I'm going to choose the new substitution variable to be v. And I'm going to let v equal u over the square root of 2. Which, by the way, it would have been possible to do this with one single substitution up here. If I wanted to, I would have had to anticipate we wanted a 1 plus something squared. We would have had to have taken out the 2 right here, which would have turned this into a 1, and would have put this over 2. And then the choice I would have made here, okay, would have had to rewrite this as e to the x over root 2 quantity squared. We would have chosen u equals e to the x over the square root of 2. All of that would have needed to have been done up there. And we could have done it that way. Right? It's, certainly looking looking ahead quite a few steps to see where we were going. The way I'm going through it right now, I am choosing to do this by a second substitution at this step rather than going back to the beginning. Okay, and demonstrating that you would need to choose a new variable then. Okay, it's a complicated example. But if v is equal to u over root 2, then we need to find dv. And dv then would be 1 over root 2 du, right? So du over root 2. Solving for du to do a substitution, this is du equals root 2 dv. All right. So here's what we have. V is equal to u over root 2. So we're going to replace this with v. And du is going to get replaced by this, root 2 dv. So here's what we have. 3 over 2 integral 1 over 1 plus v squared. And then du is square root of 2 du. So I'm going to take out that square root of 2. So 3 root 2 over 2. Okay, sorry, right? Back here again, right? Du is replaced by the square root of 2 dv, right? Okay, go back and fix that. So we have 3 root 2 over 2, 1 over 1 plus v squared dv. And now this function here, with respect to v, has as its antiderivative the arctangent of v. So we have 3 root 2 over 2 times the arctangent of v, and then plus c. Now, how to get our antiderivative here back in terms of the original variable x? To do so, we need to reverse both substitutions. So let's get this right now. Right now, this is some function of v. So now I'm going to get it back to a function of u. 3 root 2 over 2 times the arctangent of, well, v is u over root 2. So u over root 2 and then plus c. Now we have some function of u. Okay, I'll call this f1 of v. I'll call this f2 of u or something. And then this 3 root 2 over 2 arctangent, get it back in terms of x. We have u over root 2, but u back up here is equal to e to the x. So u over root 2 is e to the x over root 2, and then plus c. we now have an antiderivative function in terms of the variable x. And we can check to see if the derivative of our result would give us this combination right here to see if this is correct. So check. Okay, check this answer. The derivative of 3 root 2 over 2 arctangent e to the x over root 2 plus c. We can factor out the 3 root 2 over 2, and then the derivative of the arctangent of e to the x over root 2 is 1 over 1 plus the argument squared. The argument is e to the x over root 2. That's the derivative of the arctangent part. Then we need the chain rule, where we take the derivative of the e to the x over root 2. And then the derivative of the constant is 0. Alright, so we have 3 root 2 over 2. We have 1 over 1 plus. This is going to be e to the 2x over 2. I'm squaring this argument right here. And the derivative of e to the x over root 2, well, that's also going to be e to the x over root 2. Now let's clean this up. So we have a root 2 in the front here, and we have a root 2 in the denominator over here. So those are going to cancel each other out. Okay. We have the numerator is 3e to the x, and the denominator, we can distribute this 2 to these two terms. In the denominator, we're going to get 2 plus e to the 2x. And that is exactly our original integrand then. So, challenging example. All right, but we were able to get through it with the techniques that we know so far from this course, through the use of one and then a second, well, two substitutions in this case. We're introduced a v substitution because u was already being used. But we could have done from the start u is equal to e to the x over the square root of 2. How would we come to that conclusion? Recognizing the form of this as it looks like something over something plus something squared. It looks reminiscent of like an arctangent function, possibly an arctangent function. Right? And so we proceeded along that path. If it was for an arctangent function, the denominator must start with a 1, or it must have one of the two terms must be a 1. So you would have to factor out this 2 right here. Okay? You would have to factor out that 2, which means it has to be factored out from both terms. The second term would have to be written as a squared quantity. So it would have to be rewritten as e to the x over root 2 and then quantity squared. We would have had to have made all those assumptions then from the start if we wanted to do this by a single substitution. Okay. Let's see. Now, just because the denominator has something like a 1 plus x squared in it, that does not always mean that you're going to have an arctangent. All right, let's just take a look back at where we looked earlier. We had this example. The denominator did have a 1 plus x squared in it. All right, but if it was constant over 1 plus x squared, then the arctangent is going to come out. But instead, if we have a linear term over a quadratic, right, then what we're going to get is in fact a natural log by use of the chain rule. Right, so just to notice that there are some nuances there. Okay, it's not always clear from the start exactly what the antiderivative is going to look like. So, and that's just part of the calculus there. It is quite challenging to do antidifferentiation and integration strategy. Okay. What's something else? Natural logs show up an awful lot. Real quick example here. You have the integral of 1 over x ln x dx. Okay, let's let u equal the natural log of x. Then du is equal to 1 over x dx. And we do have a 1 over x times dx here. In other words, you might find it easier to solve for dx to get x du. So we can use those two. All right, so we have 1 over x, u equals natural log of x, so x times u, and then dx gets replaced by x du. So then the x cancels the x there, and we get our integral entirely in terms of u, 1 over u du. That's the natural log of the absolute value of u, and then plus c. U is equal to the natural log of x. So we actually get the natural log of the absolute value of the natural log of x plus c. We can check the answer. The derivative with respect to x of the natural log of the absolute value, natural log of x plus c. By the chain rule, we get 1 over natural log of x. Remember, the derivative of the natural log of the absolute value would be 1 over the argument in the absolute value. We don't need the absolute value bars anymore when we take the derivative. So 1 over the natural log of x times the derivative of natural log of x, which would be a 1 over x, and then plus 0. Okay, and that is 1 over x ln x, and that is our original integrand. Okay, so we did find the antiderivative, natural log of the absolute value of the natural log of x. All right, and how about one more definite integral? Okay, and we'll be done. Okay, the integral from 0 to 4, x over root 1 plus 2x dx. Okay, so in the denominator we have a square root function. The derivative of a square root, if we think of that, what's the derivative of something of a square root type? Okay, we're going to get 1 over 2 times that square root dx. Okay, so something like that. And then you see there's another x in the numerator. Do we use x is equal to u squared or something like that? Okay, these are all things that we might want to look into and try it out and see, first, can you transform the integrand into an integrand that is all with respect to u? And if you can, then go ahead and change the bounds. That particular approach, though, isn't going to work. I'm going to go more along the lines of the horizontal shifted approach, where we had like a combination, we had a sum inside of a square root like we saw before. And if you take then u is equal to 1 plus 2x, okay, so first of all, I guess, so du is then going to equal, derivative of this is 2 times the differential dx. Okay, so dx is equal to du over 2. All right, so we would be able to then, I'll take care of the bounds in a moment, the denominator can be written then as the square root of u. The differential dx is du over 2, but we still have another instance of x here that has to be dealt with. Now, how do we deal with that? We invert the substitution. So let's invert this substitution. If we have u minus 1 is equal to 2x, then 1/2 times u minus 1 is equal to x. All right, it's the same substitution, but inverted. All right, solve for the input variable x. The function was invertible, was 1-to-1 on the given interval. Okay, so this was something that is going to be reasonable to do here. So we solved it for x. Okay, and we already got dx as well. So that's what we can do with this x. We can replace x then with this expression in terms of u. So we get 1/2 times u minus 1 as the new numerator. And now let's deal with the bounds. So we had x is equal to 4 at the upper bound and x is equal to 0 at the lower bound. Okay? So what's our new bounds? What are our new bounds going to be? We have evaluate the upper bound at where x is equal to 4. And what do we get? 1 plus 8, which is equal to 9. For the new lower bound, we evaluate where x is equal to 0. So u of 0, which is equal to 1 plus 2 times 0, which is equal to 1. So the new bounds are going to be 1 and 9. So we have values of u. Now we have transformed the entire integral into a new integral with respect to u. Does that make it easier to integrate? Well, we couldn't integrate it the way it was written originally. Okay, let's see if we can clean this up a little bit algebraically. We have 1/2, which we can factor out, and we have another 1/2 here, which we can also factor out. So let's take out both of those instances of 1/2. That puts a 1/4 then in front. The integral from 1 to 9, u minus 1 over the square root of u, and then du. Now we have a quotient here. But this quotient, we have both of the terms of the numerator share the common denominator square root of u. So we can, algebraically, we can split these up then. U over root u minus 1 over root u. Alright, if that is going to be something that helps. And it does in this case because it gives us power functions. We have 1/4 times the integral from 1 to 9. U over root u is just the square root of u. And 1 over square root of u, okay, well that's going to give us u to the negative 1/2, right? So I'm going to write this as u to the negative 1/2. And I'm going to rewrite our square root of u as the power function u to the 1/2. And du, which must be included as well. Alright, we don't have to transform this back into x. Well, first we have to find the antiderivative, but then we're not going to have to transform it back into x because we've already changed the bounds and we can use the bounds. Okay, the bounds are correct with respect to the variable u. Alright, so antiderivatives now. For u to the 1/2, add 1 and then divide by the result. So add 1, we get 3/2. Divide by 3/2 is the same as multiplying by 2/3. So 2/3 u to the 3/2 is our antiderivative for u to the 1/2. Minus u to the negative 1/2. Add 1, right? We got power rule, right? The integral of x to the n dx, right? We get x to the n plus 1 over n plus 1, and then a plus c. And remember, dividing by a fraction is the same as multiplying by its reciprocal as well. So add 1 to negative 1/2, we get positive 1/2. So u to the positive 1/2. But dividing by 1/2 is the same as multiplying by 2. And now the bounds. We have u is equal to 1 and u is equal to 9. Okay. Also notice here I can factor out a 2, so I'm going to take out that 2. And then we have 1/3 u to the 3/2 at the upper bound, so that's going to be what, 9 to the 3/2 minus, we factored out the 2, 9 to the 1/2. Okay, so we have that. Minus, here's fundamental theorem of calculus part 2, plugging in 1. Okay. Where now this is going to be, well, 1/3 times 1 to the 3/2 minus 1 to the 1/2. Okay, so that's by the fundamental theorem of calculus part 2. 1/4 times 2 is 1/2. We have 1/3 times this. Okay, what's that going to be, right? The square root of 9, which is 3, and then cubed. 3 cubed is 27. Square root of 9 is 3, minus, and then here we have 1/3 minus 1. Okay, and here we go. All right, the 1/2 is in front of all of that. Now 1/2 times, let's see, this is 9 minus 3 minus 1/3 plus 1. So just evaluate this and we have our definite integral. So 9 and 1 is 10, 10 minus 3 is 7. Okay, so we have like 7 minus 1/3. Alright, so it's 21/3 minus 1/3 is 20 over 3, so 1 over 2 times 20 over 3, and that equals 10/3. Alright. Okay, so we were able to do increasingly more complicated, let's just say, integrals now. Now that we are able to apply the substitution technique. Okay, usually for reversing the chain rule, and that requires some ingenuity, maybe trying out and seeing if something works, and maybe updating what we're attempting. Okay. And when we do a substitution, once we choose the primary function, usually u, for the output variable of that function for the substitution, that has consequences. The choice of u also results in a dependent du differential that we're going to need to use as well. We need to replace all instances of the original variable of integration within the integrand. They all must be replaced or canceled through the use of our substitution. That might require a combination of using the differential and maybe even inverting the substitution we made. And the resulting new integral would need to be something that we can then further integrate. It should be a simplification of what we started with and not create a more complicated integral instead. And if we have bounds, a lower bound and upper bound, that is if we're dealing with a definite integral, we're also going to have to change those bounds. If we don't have the bounds, if we have an indefinite integral, then we have to remember, after finding our general antiderivative with the arbitrary constant c, we would have to then reuse our substitution that we originally selected to write the result back in terms of the original variable of integration. Okay. All right, so I will include with this a worksheet with more examples in it. I have lots of examples here, including like this. We can now integrate the square of a cosine function, a square of a sine function as well. We can in fact use the power reduction formula in order to do so. Right? Solve this. This is a double angle, right? But you can rewrite it in terms of solved for cosine squared. And if you rewrite this, solved for cosine squared, you can then use a simple u substitution to be able to integrate something like cosine squared. These polynomial products right here, you're looking for if one of the polynomials has as its derivative the other polynomial, then you're in business and you can do the substitution. And in your future courses, you might have to look for ways in which you can algebraically manipulate the polynomial expressions, as I manipulated that exponential type function in order to get that thing that looked like an arctangent. Finding ways to algebraically manipulate the integrand so that you can get it set up for performing one or more substitutions in order to get the calculus to work, for finding an antiderivative. Okay, at this point, assuming that antiderivative exists. Okay. Check out the homework. If you have any questions for me, let me know. That's it for this section. Take care.